Okay, so hopefully we're ready to rock and roll then. So we're talking about electronegativity today, and we're also going to be talking about the polarity of molecules. So there's some new terms that we're going to be learning about. So what is electronegativity? Well, that's just an ability of an atom to attract electrons. Hi, are you just going to spy on us? Yep. I just started, so I'm going to move this over 1 sec, guys. And so this is specifically the want to attract bonds when in a compound or electrons when in a bond. And so this is just a generic depiction of two atoms. One I have represented blue and one in orange. And think of these little black circles as the electrons that they are sharing. And so one atom might want them more than the other. And this measurement of how much they want them is just a scale without units. So it's a scale that goes from 0 to 4.0. So when looking at this, I just pulled a few different elements off and put their relative electronegativities. With the higher the value being the stronger the electronegativity, where do the stronger electronegativities live on the periodic table? Top right corner. What do we know about the size, the atomic radius size of the top right corner? It's the smallest. So when it's saying smaller atoms tend to have its higher electronegativity. And so we're going to discuss why this is. If we look back at that picture there of this blue and orange atom, if we are trying to attract these electrons here, what's in the nucleus? What are the subatomic particles in a nucleus? Protons and neutrons. So electrons have what charge? Negative. What do protons have? So it's the protons in the nucleus that are actually attracting the electrons. If it's a smaller radius and the distance to the electron is smaller, it's going to better attract. This is why smaller radius atoms tend to have higher electronegativity. So looking at this chart, which element has the largest value? Fluorine, which is spelled Fluorine. I know that's a hard one to spell. And its value is what? 4.0. So this is the end of the scale. So fluorine is the most electronegative element here. And the next question is asking, why don't noble gases have a value? Exactly. They don't attract electrons. Why? Well, because they aren't going to bond because their valence shell's already full. They already complete that octet. So they do not form covalent bonds. Therefore, oh yeah, that's weird. It wasn't showing. It was showing on my end. Thank you, JP. Oh, thank you. So noble gases don't have values because they do not form covalent bonds. Therefore, you cannot measure electron attraction. Okay, so are there any questions on what electronegativity is or anything about its scale? I'm hoping that today's lecture will be pretty straightforward. The higher the number, the higher it wants those electrons, okay? And so now we're going to connect this to two terms, polar and nonpolar. So when we're talking about a polar covalent bond, we still have a sharing of electrons, but the way they share is going to be unequal. Should probably make that grammatically correct there. And so the reason why is because one atom has a higher electronegativity than the other. So if you're polar, you have an unequal sharing, and this has to do with the difference in electronegativities being high. Now, if you're nonpolar, you're going to share equally. This is because both atoms have the same or very similar electronegativities. I'm going to abbreviate that. So, yes, go ahead. Exactly. And the next section here is describing where those cutoffs are, because we can assign numerical values. And you may be thinking, how can you share something unequally? It's kind of a weird concept. And all I mean is that, think about it, if you and a sibling, you share an Xbox. If you share unequally, maybe you play Xbox 3 times as much as they do during a day. It's unequal sharing, but you're still sharing the same concept together. Okay, so how do we determine if something is polar or nonpolar? And Axel was right on the nose with that, and it has to do with the differences here. And so we're also going to talk about this term ionic. And so this is what we're going to be studying next unit. But all I mean by ionic is that instead of having our non-metal, ionic bonds happen when you bring metals into the picture. And so don't worry about that term so much now. We'll discuss that next unit. But the way we can determine the bond type is finding the electronegativity difference. That's what this END is abbreviating. Electronegativity difference. And so, as it is pretty much said in the term itself, you're finding the difference in electronegativities. So when you have a small difference, and we're going to call this between 0 and 0.4, this is going to be a non-polar bond. The electrons are then shared equally. Then we're going to give this medium difference as between 0.5, we shouldn't be on computers right now, and 2.0. This bond is then called polar, or the electrons are shared unequally. And then if we have a huge difference, so greater than 2.0 difference in electronegativity, we're going to call these bonds ionic. And why these bonds are different and we're not talking about them yet is because they don't share electrons, but the electrons are actually transferred. I don't know if there's 1 R or 2. I'm just going to wing it, guys. All right. So any questions on setting up this scale? So if you get a difference between 2 atoms between 0 and 4, nonpolar, between 0.5 and 2, it's polar, greater than 2, ionic. And so we're going to practice determining those. So starting with the first one here, what I'm going to do is I'm going to open up and bring back this table here. So potassium, this is right where my pen stopped working last time. We'll see if it works. Looks like we're working. Okay, potassium, that has 0.8 as its electronegativity. Then fluorine has 4.0. And so to calculate the electronegativity difference, or END, that is equal to, now, it does not matter if you put which one you put first. I typically always put the larger one first. If you put the smaller one first, take the absolute value. Electronegativity does not go negative. So the difference is always the absolute value. For this one, it's going to be 3.2. So what kind of bond is this? Ionic, which makes sense. We have a metal and a non-metal. It should be ionic. All right, the next one, sulfur. That is 2.5. Oxygen is 3.5. So what is our electronegativity difference? It is, yeah, it is 1. So 3.5 minus 2.5 is equal to 1.0, or polar. Nitrogen has 3.0. We just said that oxygen was 3.5. So our difference is equal to 3.5 minus 3.0, or 0.5. Is this nonpolar or polar? It is polar. Right on the edge there. All right, now fourth example has 2 chlorines. What is the difference going to be with 2 of the same atom? 0, which means it's 2 of the same atom is always going to be what kind of bond? So 2 of the same atom, always 0, always nonpolar. All right, example 5, carbon, which is 2.5. Hydrogen is 2.1. So our electronegativity difference here is going to be 0.4. And also, I will not shame anybody for using a calculator on these, okay? Decimals get me thinking crazy stuff, so no shaming there. But what kind of bond is this? Nonpolar. All right, then hydrogen, we just said was 2.1. Oxygen is 3.5. So if we calculate their difference, 3.5 minus 2.1 is equal to 1.4, and this is polar. Are there any questions on how to calculate END or the electronegativity differences here? Seem pretty straightforward. We have certain cutoffs. We figure it out. Okay. So let's talk about what that means for intermolecular attractions, or the attractions between molecules. So we're first going to talk about between polar molecules. And water is a great example for this. So when I say polar, I want you guys to think of opposite poles. Think of North Pole, South Pole. They're going to have differences here. And so this kind of concept applies to the molecule, because you're going to get one side that's partially negative and one side that's partially positive. And so how we show this as scientists is we first determine, okay, in this water molecule, let's look at this bond between this hydrogen and this oxygen. What is more electronegative, the hydrogen or oxygen? The oxygen. So what we're going to do is we're going to draw an arrow from this hydrogen to this oxygen, showing who's tugging on the electrons. Who wants the electrons? It's oxygen. So this is the flow of where they'll spend majority of their time. We then draw this little hash arrow here. This is just what they do. So now, if we think about it, that's going to happen also from this hydrogen to this oxygen. There's going to be a draw of electrons. So if the electrons hang out on oxygen majority of the time, what charge do you think it'll get? A partial positive or partial negative? It's going to be a partial negative, because if electrons are negatively charged and they hang out on the oxygen more, what do you mean? Because electrons are negative. And if they spend more time on the oxygen, then it's going to give off this partial negative on that side of the molecule. So what do you think, if this is a neutral molecule, what do you think that gives the hydrogens? Exactly, a partial positive. And so what I'm drawing here is a Greek symbol sigma, and this is what they use to represent partial. And so what these arrows are showing, I'm writing arrows represent what's called a dipole moment. And so this term dipole, this just represents this partial charges that occur because of the drawing of electrons. And so what makes water and other polar molecules neat, but especially when it comes to water, is that, okay, now I put another molecule next to it. This oxygen is also going to have a partial negative, leaving these hydrogens with partial positives. What do you think is going to happen between this partial positive? Oops, and I wrote that as partial positive. Come on, guys. Between this partial negative and this partial positive, they're going to attract. And so what's really cool about water, it does this thing called hydrogen bonding. And what this means is that there's actually a temporary covalent bond. So it doesn't actually bond, but it's pretty much has the strength of that between this partial positive and partial negative. And so it creates a very strong attraction. This is what gives water, one of the reasons why water has such cool properties has to do with this hydrogen bonding. So you guys have seen bugs run across the surface. It has to do with how much water likes itself. And so what's really neat is now if we think about water in its solid phase, ice, what happens is these molecules arrange themselves similarly as below, where they create these pockets of space in between themselves. This is why ice floats on water, because when it's in solid state and it moves and transforms itself into this lattice, creating these pockets, it allows air to be in there and creates ice to float. So this is why ice is less dense than water. Any questions on dipole attraction or dipole moments, partial positive, partial negative? Another hint I want to give you guys. If we look at this arrow, what does this part of the arrow kind of look like? A plus sign. That's the side that gets the partial positive, okay? So this is kind of a trick to remember that. Yeah.
Are they ever negative?
What do you mean?
Like, you know how you see it's like partial positive?
Yep.
Are they ever negative?
Like in this molecule?
No. I mean, you know, like how would you know if it's going to be positive or negative?
It has to do with the electronegativity. The higher the electronegativity, the more it wants electrons, it's going to be partial negative. So think high electronegativity, partial negative, but this only counts for polar molecules. So that difference has to be greater than 0.4 for this to apply. Axel, do you have a question too?
Yeah, so why do you put that little hash through the arrows?
That's just what they represent. And it's to represent electronegativity. Versus like if I just draw an arrow, it could represent a bunch of different things. The second I put that dash through, you know we're talking about the draw of electrons. Any other questions? Awesome. Okay, let's talk about nonpolar then. So this is acetylene. This is actually what welders use. This is the gas they use in their torches. Now, if we think about the electronegativity difference between hydrogen and carbon, what did we determine that was? What type of bond? Nonpolar. What about if we have two carbons? Always nonpolar. If you have two of the same, their difference is going to be 0, always nonpolar. And then another nonpolar here as well. So this is a very nonpolar molecule. This means that no atom is really pulling for the electrons, so you're going to have no partial charges. However, nonpolar molecules have what are called dispersion forces. And what dispersion forces are, I'm going to make this note here, is they are weak. They're hardly an attraction, but they exist. And all it has to do is, if we're sharing these electrons, the electrons are moving around the molecule, maybe for the briefest moment of time, more electrons end up on this end of the molecule, and very quickly, this end becomes negative from the electrons. And then that might have some sort of attraction to another molecule. So super brief, but it happens, but it's very weak. And so that's called the dispersion force. All right, any questions before we talk about solubility? Okay. So last thing is talking about solubility. And what this means is, okay, so nonpolar and polar solvents, they don't dissolve in each other. Only like dissolves like. So this is a phrase I want you guys to remember. What that means is nonpolar solvents dissolve nonpolar things. Polar things dissolve polar things. And so I think this video that I'm going to play is a very awesome representation of this. I'm a very visual person. And so describing kind of the parts that you'll see in this video. You will first see that you have 3 different solvents. Ethyl acetate is nonpolar. Water is polar. And chloroform is nonpolar. Then iodine is a nonpolar solute. So all a solute is a solid that you add into solution. Now copper 2 sulfate is ionic. And so we will talk about that after this video here. So what I'm gonna do is oops, I need to fix this. Hold on. Okay, what in the world? Where'd my video go? Okay, perfect. Okay, and it's got some real cool music, you guys. So what it's showing you right now are the 3 solutions. And so they're not mixed together. The arrows are pointing to where they're separated. So now they're taking the solutes and adding them to each layer. And so notice they don't mix with all 3. So hopefully you guys can hear me now. I'm back just on my computer. If you guys have any questions, let me know. Everything's posted on Google Classroom.
Mr. Fair, I take that back. I do need that code.
Oh, okay, that's okay. Let me look it up here real quick. When you're ready, let me know.
I'm ready.
Okay, it is
Mhm.
RLCOMON.
I like screen